Okay, so our final lecture, this module, lecture 12, we'll be talking about multiplexing. It's a very brief lecture. We're going to go through a few concepts, a few examples, then we're going to talk about the exam, a little bit about the class test, and then the plan for the final few slots. So last time when we met on Monday, we spoke about digital bandpass modulation, so digital wireless modulation. And we said there are three things that we generally change, and that's the amplitude, the frequency, or the phase of the carrier. So we can either change the amplitude, we can change the frequency, or we can change the phase of the carrier. So we have our amplitude shift keying, our phase shift keying, and our frequency shift keying. We spoke a little bit about modulation and demodulation of each of these. We spoke about variations such as quadrature amplitude modulation, QAM, and different types of ASK, so 2 ASK, 4 ASK, or as we like to call it, M ASK, or M ARRI ASK. And we spoke a little bit about the advantages and disadvantages of all of these. Okay. So where are we? We're on our final lecture. And this time next week, we will have our class test. Okay, so a 2-hour class test, this time next week. Okay, so there will be a, I call it a problem class. It's not really a problem class, but let's call it, there's going to be a problem sheet for Monday. We will meet, we'll go through some of these questions together, and there'll be a Q&A session where I'll answer questions. But for Monday, there won't be a lecture, okay? There'll be a problem sheet, there will be YouTube videos, and I'll be around to answer questions. Okay, after we've had the class test, so after Thursday, I will release two things. So I will release a practice exam and past exams. Okay, so you might find the practice exam more useful than the past exams, because the practice exam will be the open book style exams, whereas the past exams will be more closed book numerical style exams. But I'll release each of these right after the class test. The reason I'm waiting till after the class test is just not to confuse you, not to clutter issues. So the class test, I won't be asking the kind of things I'll be asking in the open book test. So open book test is completely different. The class test will be just like your practice questions. So really straightforward numerical questions mostly. Okay, so the class test is a 2-hour test, this time next Thursday. Now, I've said several times before, and I'll remind you again, if you can't make it, if you're unable to make it for that test, let me know. I'll reschedule another test for you. Okay, so I've already been told some people might be traveling that day. And if that's the case, you're unable to take the test, I'll set another test for you. But I need to know. You don't just not turn up for the test and then say, reschedule it for me. Tell me as soon as you think you're unable to attend the test. Okay. The 2 hours, people who have extra time will get extra time. Okay. So when I say 2 hours, it doesn't mean it's a 2-hour test. It's still roughly a 45-minute test. Okay, the 2 hours is to give you enough time to log into Vital and take the test remotely. So under remote circumstances, you might not have a good high-speed connection, you might have difficulty getting into browser, your computer might crash a few times. So I'm giving you that extra time, but it isn't a 2-hour test, it's just a 45-minute test. But people with extra time will still get the extra time, and the extra time will be counted on the 2 hours. So if you get 25% extra time, then it's 2 hours times 25%, all right? So you get 1.25 times 2 hours. Okay, multiplexing. What's it all about? So remember, in communication systems, we said we have a transmitter, a receiver, and a channel. Now, if we want to be more efficient, if we want to use the channel more efficiently, then it would be good if we could have more than one party communicating, or one pair of parties communicating at the same time, using the same channel. So what we're trying to do is to share the channel between multiple parties. So we can have this guy communicating with this guy, while this person is communicating with this person, and this person is communicating with this person, sharing the channel. And there are different ways to do that. We can either share time, or share frequency, or share both. Okay, there are other ways, but these are the broad categories. So if you look at this little animation here, so we have conversation A happening between these two parties in red, and conversation, say, D, happening between the parties in green, and somehow they're using the same channel. They either take turns, each person or each pair of parties taking a slot, a frame, a time slot, or they're operating at different frequencies. But the whole point of multiplexing is we are sharing this common resource, which is the channel. It can be a physical channel, or it can be an electromagnetic radio channel. But we're sharing the channel either in time or in frequency, or on both. So we have a multiplexer, MUX is the abbreviation, and a demultiplexer at the receiver. Now, when we spoke about digital communications last week, and then the week before that, or the last lecture and the lecture before that, we spoke about something called bit error rate. Maybe not using that language, but we introduced this idea of bit errors. A bit error is an error in a bit. It's a bit that's arrived incorrectly. So a bit that was transmitted as a 1, but then arrives as a 0. So something has happened on the channel to cause that error. And by quantifying that, by dividing or creating a ratio between how many bits we receive in error to the total number of bits, we have this figure called the BER, the bit error rate. It's a very common measure to compare digital modulation schemes. So it's used for comparison purposes, right? So when we say performance quantification, we want to see how good a communication system is. So in this example, we have this red communication system and a blue communication system. The red and the blue could represent different modulation formats. For example, the horizontal axis is the signal to noise ratio, and the vertical axis is the bit error rate. So you would want the bit error rate to be as low as possible. So what am I doing there? So we want this to be as low as possible. So if you want to compare these two communication systems, for the same signal-to-noise ratio, A has a lower bit error rate than B. So A is better, because for the same signal-to-noise ratio, you get fewer errors. The number of bits received in error is fewer. Now, that doesn't mean we can't achieve the same performance. We could achieve the same performance, the same bit error rate, by increasing the signal-to-noise ratio. But if we don't want to waste that power, if we want, for a given signal-to-noise ratio, we get a better performance with A. Okay, so it's possible to achieve the same performance with B by improving the signal-to-noise ratio, but A is a better performer at a given signal-to-noise ratio. So that's how we'd interpret graphs like this. Now remember, last lecture, we asked the question. We said, when we increase the number of bits per symbol, it says number of symbols per bit, but it's referring to the same thing. So when we say the number of symbols per bit, we mean per bit period. So maybe the best way to interpret this sentence is when our error is more or less likely when the number of bits per symbol increases. So for example, if we're comparing binary ASK to 4 ASK to 16 ASK, where is it more likely that the receiver will make an error? Where is it more likely that we get bit errors? So remember, we said as you increase the number of levels, so if you have 2 levels compared to having 8 levels, your thresholds, here you only need 1 threshold, whereas here you need 7 thresholds. So the possibility of error increases as you increase the number of bits, as you increase the number of levels. So here, as we go from 2 up to 64 QAM, at the same, if we take this, this is the same as signal-to-noise ratio. So as a what I should have probably written was signal-to-noise ratio because it's in decibels. So at a given signal-to-noise ratio, compare these. Which is better? So clearly, this is better and this is worse. Why? Because this is bit error rate. Okay, so that's 1. So 1 means that you have 100% error. Everything you receive arrives in error. So as you go down this axis, it's better. So clearly, this curve here is better than this curve here. And this curve here was the 4 QAM. So it says, so to answer the question, which is more likely, are errors more likely? The answer is yes. And the why, it's all about quantization levels, resolution, noise. Okay, so that was just an illustrative example. This is a numerical example. So this is a kind of question you'll see in the class test or in the problem sheets. So what are we looking at here? We're looking at a plot between bit error rate and signal-to-noise ratio, exactly the same. So these three, all the same. What are we looking at here? ASK. So here we're back to bandpass modulation. Okay, so we're looking at ASK and FSK. What does BFSK mean? So BFSK, the B just means binary. So that just means 2. So ASK and FSK. So before we answer this, forget the question for now. Just looking at the graph, for a given signal to noise ratio, which is better? Which is the best of these modulation formats? Which has the lowest bit error rate? So if you just draw a line through there, clearly it's the green line that's the best. Of these 4, it's the green, which is the BPSK. Why? Because it has the lowest bit error rate. Now, the question is actually a numerical one. How much more likely? That means by what factor? How much more likely? That means by what factor? So how much more likely are we to receive a bit in error using ASK compared to DPSK? So we're looking at the blue and the red. At a signal to noise ratio of 9. Okay, so let me clean that up. Okay, so we have a signal to noise ratio of 9. So that's that there. So at that signal to noise ratio, how much more likely are we to receive a bit in error using ASK compared to DPSK? Well, at ASK, you have a bit error rate of 1 in 100. And for DPSK, you have a bit error rate of just over 1 in 10,000. So what's the answer? Is it 10 to the minus 2 minus 10 to the minus 4? No. We're looking at the factor. So you divide. So how much more likely? So you divide, it's a ratio. So what we do is you divide. It's 100 times more likely. So if you receive a bit, 1 bit, with a signal to noise ratio of 9 decibels, 1 bit of ASK is 100 times more likely to be in error compared to DPSK. Okay, I hope that's clear. All right, so deconcept 10 times. Maybe there's another 0 there. 100 times, yes, 100 times. Okay, so we still haven't really spoken about multiplexing. So multiplexing is a way to improve the efficiency and the privacy of your communication. Efficiency, that means we're able to transmit more bits per second through the same channel. And privacy, so that communication is less easy to intercept and less exposed, because you have multiple parties sharing the same channel. So if you were to intercept the message, you would have lots of conversations all mixed together. So you can think of it as one shared resource and then multiple parties all queuing up to use it. So we've already mentioned that we have a multiplexer, demultiplexer, and a channel. So this is just a bit of terminology. More terminology, we have something called simplex and duplex. So simplex communication is one-way communication. Half duplex communication is one-way communication both ways. And full duplex is two-way communication. Okay, so think of it think of the example of a radio. So a radio is one way. You have the broadcaster transmitting, the radio is receiving. That's one-way communication. A half duplex, you can transmit in one direction at one time. So it's like a walkie-talkie. You can talk, the other person listens. But while you're talking, you can't be listening because the channel is only used in one direction at one time. Whereas in a phone call or in today's online lecture, we have full duplex. So I can be talking and you can be talking at the same time. Okay, so obviously this is the most versatile type of channel, but there are situations where we want simplex channel. Okay, so remember we said that in a multiplexed channel, we can either share frequency or share time. Generally, when we talk about frequency domain multiplexing, where we share frequency, we're talking about analog communications. And when we talk about time domain, it's generally digital communications. Okay, it's not exclusive, but that is generally the case. Okay, there's other types of modulation. We sometimes talk about wavelength division multiplexing, code division, multiple access, CDMA, which is a form of spread spectrum. We'll say a few words about that in a minute. So in frequency division multiplexing, all the time, a channel is used exclusively at a particular frequency. So each frequency band is assigned to a particular channel or a user pair all the time. Whereas in time division multiplexing, each user is given a single slot in time. And that, while the user is using that slot, they can use all the frequency. But that slot repeats. So it's that slot, then it's repeated here, then it's repeated here, then it's repeated here. So what we have is these frames. Each frame consists of slots, and each slot is allocated to a user. So again, terminology. When we talk about frequency division multiplexing, we use the word channel. Okay, so this is generally an analog channel. So this is generally analog. It doesn't have to be, but it can be analog. So channel 1 will be assigned this frequency range, channel 2 will be assigned second frequency range, channel 3 the third frequency range. Sometimes there can be some overlap, very slight overlap between these channels. Sometimes we want the opposite. Sometimes we want each channel to be separated from adjacent channels, and we have this guard band between adjacent channels. Okay, so when we say channel, we're not talking about the electromagnetic channel, we're talking about the part of the electromagnetic channel that's assigned to each user. So they share the frequency axis all the time. So they're using the that section of the frequency axis all the time. So think of it like a radio station. When you tune into one radio station, all the other radio stations are still broadcasting. When you're watching one television channel, all the other television channels are still broadcasting at the same time, but they each have a different frequency channel. They're all talking at different frequencies. If you were on a walkie-talkie and you turned to channel 2 and you were speaking to someone on channel 2, other people are still talking on channel 1. It's just you can't hear each other because you each have a different frequency channel. You're all talking at different frequencies. So you have different carrier frequency, you might have different bandwidths. So that was an illustration of frequency division multiplexing. As I said, it applies to broadcast like television, radio, and even some high capacity phone lines. And when we speak about the electromagnetic spectrum, we'll speak about the different portions of the electromagnetic spectrum. This is also a form of FDM, where all these different applications, whether it's satellite communications or GPS or Bluetooth and NFC and radio, they're all sharing the electromagnetic spectrum at the same time. That itself is a form of frequency division multiplexing. So that includes analog and it includes digital. But TDM is generally just for digital. So again, examples of FDM and FDM, different bandwidths. You can have same bandwidth, you can have different bandwidths, you can have adjacent spectra, overlapping spectra with very slight overlap, or more commonly you have guard bands. Now, time division multiplexing is different. Time division multiplexing is generally for digital communications, and it's where we allocate time slots. And it's really important. So what you have is you have a clock, and that clock samples each of your signals. So assuming that your signals are analog, you would need a clock to sample them. If your signals are digital, then you don't need that. So if your signals are analog, you need to sample them, and the clock rate, the sample rate, needs to be at least the Nyquist rate for the highest frequency amongst them. So if you have here conversation A, B, C, D, E, and let's say E has the highest bandwidth, then your sample rate will have to be at least the Nyquist rate for conversation E, meaning even if E is critically sampled, A, B, C, and D will be oversampled. So you can't have different sample rates for different conversations. As you can see, it's the same clock. In more advanced TDM systems, what you could have is you can have more than one sample per frame, more than one slot per frame for a high frequency message like E. It could be, instead of having 1, 2, 3, 4, you could have 4, 3, 4, 2, 1, 4, 3, 4, 2, 1. So you'd have two slots from conversation 4. But we're not looking at that. In this module, we'll assume that we have the same clock rate, the same sample rate, even if the frequencies are different. Right? So the bit rate of the medium, that's the channel, will be considerably higher than the data rate. Well, two things. Each message will be sampled, and you're having fs times n bits for each message. But because you have several messages, you have, in this case, 1, 2, 3, 4, 5 times n times fs bits per second on the channel. And we're just saying that the bit rate of the medium is higher than the data rate of the signal. So that's almost by definition, your channel capacity has to be greater than or equal to your data rate. Again, a quick little animation to illustrate this. So that was time domain multiplexing, where different channels or different users share the channel by dividing up time between them. We've spoken about frequency domain multiplexing. There's another kind of multiplexing where you use all the frequency axis at different points in time. So rather than having a single frequency channel all the time, or all the frequency channel at different times, we have portions of the frequency channel at different times. So we call this family of multiplexing schemes spread spectrum, because we spread the communication over the entire frequency spectrum. So rather than using a single portion of the frequency spectrum, we divide it over all the frequency spectrum at different points in time. So imagine two parties needed to communicate a very critical, secret message. Okay, so they're using analog communication and they're trying to communicate. So imagine in a war scenario where a commander is communicating with their troops, and the enemy wants to intercept that message. If they're able to intercept the frequency, if they're able to tune into that frequency and intercept the message, then they are able to receive the communication. So in the same way that every instant in time a different frequency is emitted here with this little analog music box, in the same way here, if you look at the spectrum analyzer at the top, you look at the different frequencies, you look at the center frequency moving in time, you have a very similar effect. And in this third little video here, it's just illustrating, this isn't Bluetooth, but this is
okay,
an example of frequency.
Anyone
hopping.
Who wants to know what extreme hopping
So that's
looks
a
like,
frequency analyzer, spectrum analyzer.
or
that's not a time domain.
EZUHF.
So that's frequency hopping happening in real time.
So center frequency is 440 megahertz. So,
okay, so those were just illustrations, really. So, few final words about spread spectrum. Okay, so we're not going into any detail. I simply want you to appreciate that spread spectrum technology is what we use for our highest frequency communication. So we're moving from 4G to 5G now, and 5G is all about CDMA, which is a form of spread spectrum. Wi-Fi, Bluetooth, Wi-Fi 6, all of this is spread spectrum technology. So when we talk about TDM, that's generally for digital telephones. When we talk about FDM, it's for analog sharing of the frequency channel. But spread spectrum, that's all for our high speed digital communications. Okay, so all of these applications rely heavily on different forms of spread spectrum. Not always frequency hopping, but it's the same general idea. Okay, so that's all you really need to know about spread spectrum. If you want more information, if you're interested in digital communication and advanced digital communication, or if you're on the communications or the telecommunications program, then there is a third year module given by Dr. Judy Zhu, ELEC477, ELEC377, and she goes into all of these in great detail. So it's digital and wireless. So it's only band pass communication and it's only digital communication. So it's basically the last two lectures in this module in great depth. So it's 15 credits that she goes into all of these things in great detail. Okay, so that really is all we have to say about the subject of multiplexing, and that's the end of this module. So that's the end of today's lecture. I want to say a few words about the exam or the exam replacement. So you know the exams have been cancelled and we have exam replacements, but we're going to use the word exam to replace the word exam replacement. Okay, so whenever I say exam, I'm talking about the exam replacements. So they will look like normal exams, The front page will be very similar to a normal exam, but you'll see the word replacement there. There was a mock exam, a practice exam released on Tuesday. I hope you've all managed to see that. I encourage you all to go download that paper, have a go. You don't take the paper too seriously, but do download it and try to write something. It doesn't matter if it's a correct or incorrect answer, but write something and upload it just to see how the system works, to make sure that you're able to connect to Vital, make sure that your browser works with Vital, make sure your app is working, make sure you're able to arrange the papers in the right order and to scan correctly. I think it's a good idea to use the time you have from now until Monday to at least make one attempt to upload it, the mock or the practice paper. I will be providing a practice paper for ELEC202 next week, okay? Now, the actual exam will look like any other exam, 4 questions, 25 marks each. But instead of having 2 hours, you have 48 hours to do the test. It doesn't mean it's a 48-hour exam. It's still maybe a 2 or 3 hour exam, but there'll be fewer numerical questions. Okay, so don't expect me to say, find the sampling rate or calculate the channel capacity, because we've already asked those questions in the class test. I'll be asking you to design something, to explain something, to compare, to discuss, to contrast, to plot, to sketch. So you'll need to be a little bit more creative, a little bit more imaginative, okay? So they won't necessarily be difficult. I won't ask difficult questions, but the questions will be unfamiliar. They will be strange. They won't be the kind of questions you would expect in a class test, okay? I'm deliberately giving you a practice test to show you the kind of unfamiliarity to expect. So that doesn't mean the actual exam will look like the practice paper, but the kind of unfamiliarity, the kind of strangeness, the kind of weirdness, the kind of creativity I expect in the exam is very similar to that you'll see in the practice paper next week. Okay, so there won't be any textbook solutions. You won't be able to Google the answer. Okay, I'm not expecting you to go to the PowerPoints and just copy and paste a solution, because there won't be a solution to copy. Okay, but don't let that worry you. It doesn't mean the exam is necessarily going to be more difficult. It shouldn't disadvantage you at all. If you're worried about your handwriting, then just type it, use a word processor, and type the answers, and that should be fine. Okay, so I hope you actually find the exam fun. I tried to make it enjoyable for those of you who enjoy communications. When you see the practice paper next week, you'll know what I mean. I'll be around to answer any questions or to help. Make use of the discussion board. There are a few questions I haven't yet answered on the discussion board. I'll do that this week going forward. Okay, so that's a little bit about the exam. That's it. You've come to the end of the module, so well done for surviving this far. I hope you found it useful. Remember, I promised at the beginning of the module I would try to make it as relevant and as useful, as helpful, and as enjoyable as possible. I hope I've managed to do that, despite all the craziness that's been happening and all the changes and arrangements. But the fact that we're not meeting face-to-face doesn't mean that I'm not going to be around. I will be here to help you, support you, answer any questions you have. I've enjoyed teaching this module. I hope you found it helpful too. We will meet again on Monday for some Q&A and to talk through some questions. But before that, there will be some YouTubes going through the final problem sheet. I forgot to tell you that we have one final problem sheet and one final practice test, and that will cover lectures 11 and 12 with a focus on lecture 12. So lectures at 11, it doesn't lend itself very well to short numerical questions. So there won't be a practice test or a problem sheet about lecture 11. And by extension, there won't be questions about lecture 11 in the class test. But lecture 11 is sort of included in lecture 12 anyway. Okay, so before we go, are there any questions? Does anyone have any question about today's lecture, about the exam, about the class test, or about anything else?